So my name is Michel Quintard. I am a CNRS Research Director at the Institute of Fluid Mechanics in Toulouse, and I'm going to talk today about multi-scale analysis of transport phenomena in a porous medium. Even a simple porous medium, for instance, a manufactured medium in a chemical reactor, for instance, is already a multi-scale system, and it is often described, and I will draw the following picture. So I have what I will call the pore scale here, typical structure of a porous medium with different characteristic scales. For instance, I will use this notation small l, and this is part of a larger system, which is, for instance, in chemical engineering, my porous column, my chemical reactor, which has a characteristic length which I will denote as a capital L. This is very simple, but already a complicated system. If I am interested in transport of a property over the pore scale, of course, this is very difficult to describe because the geometry is complicated, and especially there is something which is very important in multi-scale analysis, which is the ratio between the small scale and the larger scale of the system. And in most applications, I will have this sort of separation of scale. Small l is much lower, much smaller than the large scale. Well, what is multi-scale analysis? Multi-scale analysis is trying to describe flow at this scale by introducing an intermediate scale, which is, we can denote that by many different stuff, but I will use R0, which is the scale of something which is often called a representative elementary volume. So multi-scale analysis is essentially going from one scale, for instance, I have pressure and velocity, and trying to define large-scale properties, and I will comment on that later, for instance, some sort of macro-scale pressure and macro-scale velocity, and trying to find a relationship between those two. So I have equations describing those properties at the pore scale, and I want to know the equations there. Why is it useful? This is useful because, of course, I don't have, if I am able to exhibit the macro-scale equations, then I don't have to solve for the pore scale problem anymore, and that's very, very, very efficient. So that's the advantage. The difficulties are essentially related to the fact that I have to have a separation of scale. So I have to have this sort of inequalities, and this is not always the case. There are many systems which are not, which do not obey this kind of feature, and in particular, this is the case for many geological material because the natural process, geological processes are such that I have a series of intermediate scales, and I will complicate it a little bit, this figure, by introducing intermediate scales in which I have another description, another type of heterogeneities, which is associated to the geological processes for sedimentation, for instance, and so forth. So therefore, and this is where the name multi-scale analysis takes its full meaning, is that I have possibly intermediate steps, and there might be many of these. And once again, I can apply this idea. I have the equations on the lower scale, I get the equations on the upper scale, and I get the equations, subsequent equations in the system. But as I said before, well, maybe this separation of scale assumption is not satisfied, and this is the big questions. The big question for multi-scale analysis. Well, still, we can use the results obtained by assuming there is a separation of scale, but of course there will be an error doing that, and what is at stake when you do this sort of modeling is to understand the errors which are made when applying that to the real world. But in all the time, this is what is done For instance, in reservoir simulation for petroleum engineers, which is done in hydrogeology and in any application that use systems which are heterogeneous in nature.